Alright, well today's going to be a rather short video, so you might want to watch today's and then watch the next one. Maybe get a little head start on the next one because I know it's going to be significantly longer than today's. So today is just about prime numbers, and we do need to have this discussion about what a prime number is because it does show up in some theorems and stuff later on. We all know that a prime number has to be bigger than 1, first of all. And the only two positive numbers that divide it are 1 and the number itself. So that's what a prime number is. And then if it's not prime, we know that it's composite or composite or however you want to say it. I think I've learned to say composite. And so we have Euclid, who had a lemma. It's kind of like a mini theorem. It's something that you need to prove before you prove an even bigger theorem. That's what a lemma is. So Euclid's lemma for prime says that if you've got integers a and b and you've got prime p, well, if you multiply those together, a and b, and you get something that p divides into evenly, then that means that p either goes into the first number or it goes into the second number. You can say, for example, 6 and 5. Let a be 6 and b equal 5, and let's let our prime number be 3. Well, 6 times 5 is 30, so this says that if 3 divides 30, then either 3 divides into the 6 or 3 divides into the 5. And you know that 3 divides into the 6. So just kind of a simple example of that lemma to help it make more sense to you. The second lemma doesn't have a name, but it's kind of an expansion of Euclid's lemma, and it basically says that if a prime number goes into a bunch of integers that are all multiplied together, and they're all bigger than or equal to 2, then p has to go into at least one of those factors. It just says that there exists one, but there could easily be more than one of those factors that p goes into evenly if it goes into the product of all of them multiplied together. So that's lemma 2. And then here is the fundamental theorem of arithmetic. Basically says every positive integer greater than 1 is either prime or it's expressible uniquely as a product of primes. And you've done prime factorization before using a factor tree or using repeated divisions, where I give you a number and you can express it uniquely as a prime factorization. And then one last thing, this is kind of interesting. If you have a composite number, then that number does have a prime divisor p, such that p is less than or equal to the square root of the number you're dealing with. So take any number, 150. It's composite. You know that there's got to be some kind of prime factor of 150 that's less than the square root of 150, which is like 12 point something. So you know that there's going to be a prime divisor that's less than 12. That's all I wanted to say on prime numbers, but we'll have more discussions on this tomorrow. And please email me if you have any questions.